This GVEW, that is a representation of a graph.
We are not the god.
Well, you are.
Yeah.
I mean,
If the graph given to us by the teacher model is good enough, and that's what we are showing.
record of it.
Yeah, sure.
Okay, cool.
So
Sorry.
this is an amplifier. I'll just restart again.
Right.
So we are solving the problem of pre-layout designing. And we start with a schematic. The designer gives us a schematic and some specifications associated with it. Like let's say this is an amplifier, so gain has to be higher than this value. The unity gain bandwidth must be greater than this, and all of those specifications. But at the same time, make sure that the objective function is also kind of minimized or maximized, depending upon what the objective is. So how do you solve this problem? So we have divided this whole thing into 3 stages. First is called as graph of circuits. Second is the graph surrogate model. Third is the constraint optimization. Now let me just go through the whole pseudocode of it. So first step is learning a graph. Second is doing a label propagation on the unlabeled instances. Third is generating a surrogate model, and fourth is the constraint optimization. Let's go on to the first step. So the general literature around this particular work has been is that when you have this particular schematic, consider this whole thing as a graph. So what you do is make multiple such graphs. So it becomes a graph regression problem. The label will be gain, UGB, gain margin, phase margin, corresponding to each of the circuit instances.
I have a question about the creation of the graph.
Yes.
What are the nodes and what are the edges?
According to the literature, each node is going to be the circuit component, resistance, capacitance, transistors, all of those things. But as I mentioned, you have to generate multiple such graphs, and it is always going to be a supervised setting problem. So obviously, it is going to be computationally very expensive. Generating those labels is also going to be very cumbersome task, right? So what we are saying is reformulate this whole thing into a node regression problem and a semi-supervised learning framework. How do you do that? Instead of taking this whole thing as one graph, consider this thing as a whole feature vector, right? So these are multiple such feature vectors, and generate labels only corresponding to few samples, keep most of them as unlabeled. Now, how do you generate a graph out of it? This GVEW, that is a representation of a graph. This W corresponds to the weighted adjacency. How do you get that? By solving this optimization formulation. It has 3 steps. First is called as the directionless energy. So what it says is the circuit instances where the difference between the features is pretty less, make sure that they are connected with very high weights, right? So that is the first term. Second is the sparsity term. You don't want the graph to be very dense or fully connected. So you are incorporating a sparsity term. And the third one is the regularizer, just to make sure that your weights does not go down to 0. So from here, you end up with a graph where you have some samples which are labeled. Most of them are going to be unlabeled. Second part. So this completes our first task. Yes.
What's the node here?
Node is going to be a whole circuit.
Oh, a whole circuit.
Yes.
Okay.
This will have these feature vectors like maybe all the design parameters like VDD, the width of your transistor, length of the transistor, all of those things. That will contribute to the one feature vector of a node.
And then the X's are what exactly?
Feature vectors, that is the design matrix. So as I mentioned, like let's say this is a circuit which you have in hand.
Yeah.
So the VDD, so it can go to 1, 2, 1.5, 2.5. All these real values are going to be VDD. So these will contribute to different instances. Similarly for W1, it will be maybe 100 micrometers or 200 micrometers, something like that. So that will be another row. So something like that. So these,
It's a stack of all the bit.
yes.
But so the I and the J are going to be different instantiations of the
So this
circuits.
is Xi and Xj. So in that way. So it is going to be ON square times. So because each one will be computing with all the different features available within that particular stack.
Yeah.
Right. Now, why do you need a surrogate model? So the problem with generating labels here is, now let's say you take a feature vector. This feature vector is your one circuit. You pass it through a simulator. As the circuit size increases, the chances of generating one particular label may go up to, it take time up to maybe 30 minutes or more than that. As the circuit size increases, it can go up to hours. So you can understand, if I just want to generate a label data set for 1000,
like some voltages.
gain, UGB, gain margin. So all of these are labels. So it's a multi-label scenario. So generating just a label data set of 1000 samples will take maybe weeks, right? So we don't want to do that. So we have to come up with a way which kind of approximates the working of a SPICE simulator. And that is done by this graph surrogate model. So now what you do is, you take this graph with few labeled and most of them unlabeled, pass it through a GNN. GNN will train only on the labeled sample sets and do the label prediction corresponding to the unlabeled ones. So this is how you come up to the third step, second and third. This YU is the label prediction, so which you can see over here. And once you have done that, you have a GCX GNN, which is your graph surrogate model, which is going to serve the purpose of your SPI simulator. Now, the fourth and the final step. Take this surrogate model, incorporate it with some constraint optimization formulation like IASCO and ASTROC, and get the most optimal design parameters. So here, for constraint optimization, we are proposing two algorithms. First is the IASCO, which is also called the static optimization framework, and second is the ASTROC, which is the dynamic learning framework. So let me first explain what is IASCO. So you can see this one. This is the stack, which is the first step here, right? Generate a graph by using that particular formulation. Next, train a GNN on it, get labels corresponding to all the samples. This is the step. Now, let's say originally your graph was 1000 nodes. Now you observe that out of the 1000 nodes, there are just 20 nodes which are satisfying all those constraints. But can you say that they are going to be the most optimal ones? No, right? So what you do is take these 20 nodes and compute the bounds on the features of those particular nodes. Pass it to the D algorithm. That D algorithm will minimize your objective function and give you one or maybe some multiple solutions based on the convexity of your objective function, right? But now these particular new solutions which you have will not have the labels. So so it again becomes this particular problem. So what you do, you learn a graph and do the label prediction, and you will most assured get these solutions that these optimal design parameters will have the labels which have satisfied all those constraints, and as well as the objective function is minimized. But what is the problem? Why do we not stop at this particular place? The reason is, as the specification size increases, we have observed that the chances of getting those particular nodes might end up to 0, right? So initially I mentioned that there might be 20 nodes, but what if the number goes down to 0, right? So in that case, we need some other alternative, and that is the dynamic learning framework. So what we do here is, we start with all the label samples, but very few label samples, just 20 or 50, right? You re-rank those samples based on what criteria? Based on the criteria of the probability of the satisfying constraints, the samples which does that should be placed at the highest of the stack, right? So take just few samples out of it. Now, pass it through the D algorithm, get new feature vectors, but you don't have the label for it. It again becomes this particular problem. Get the labels using the GNN. So now you have this particular problem where the stack is completely labeled of maybe just 50 samples. Again, re-rank it. Again, pass it to the D algorithm. Keep doing it until you have started from a space which was uniformly sampled across the D-dimensional space, but now you're converging towards a space which will most probably give you the most optimal design parameters. Put an iteration budget, or maybe make sure that the difference between the loss functions or the objective function is whatever that can be the iteration budget for it, and at the end of it, you're going to get the design parameters which have satisfied all the specifications, and at the same time your objective function is also minimized. This is the whole work.
Very cool.
Yeah, thank you.
So may I just try to say this again, like based on my understanding?
Yeah.
So you may have certain, let's say, a certain number of circuit instances.
Yes.
And you don't know whether it satisfies this problem or
Correct.
not. But you can construct some features, right? Like some design parameters, and use these design parameters to solve this problem, to connect all of the circuit instances into a big graph, kind of. Each node corresponds to one circuit instance.
Correct.
Right? And you also have the node features correspond to these features, and also node labels. Only a very few number of circuit has the labels here.
Correct.
And then you use GNN as a kind of semi-supervised learning way,
Right.
to train on those labels.
Right.
Okay, and then you also get some labels for maybe those other
Unlabeled ones. Yes.
Okay.
Yes. Correct.
And then I lost the rest of the thing. Yeah, so I keep this point.
The question is, do you just assume you have some labeled ones, or are you also, depending on the graph, deciding which ones are the most optimal to label?
No. The labeling is done in a random way, because obviously we don't know where the optimal solution will lie.
But can you do the graph without the labels?
Yeah.
So
The graph
then
is just
technically you could decide, okay, a very central node is the one that I should get my label for.
maybe
Or do
that
you?
can be another
Yeah.
approach.
The
of
question
doing it.
is, can we optimally decide which labels we should have so that the
Yeah.
information is maximized?
Exactly, right?
Correct.
Okay,
Yes.
but you just assume you have some kind of random labels available. Okay, and then you go on and you have two different methods, but
Yes.
in one essentially you say, let's train a re-ranker on
Correct.
these things.
Correct.
And whenever we run out of labeled samples, we just kind of make some more and use the GNN to
Right.
label those.
Correct.
And then we
Correct.
re-rank again.
Right. Right.
And so we try to go up, up, up.
Correct. Correct.
Okay.
So
Yeah.
I have a question here. So here you will have some labels,
Mhm.
some label Y for, let's say, those unlabeled nodes.
Correct. Correct.
And then I lost the rest of the thing,
Okay,
like
okay.
how.
So,
Yeah.
what- yeah. Yes. 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 Okay. So the thing which you're saying, we have reached here. Correct.
Mhm,
So now what I was saying is, let's say you had a graph of 1,000 nodes.
mhm,
Okay. Now you generate. Now you observe that there are only 20 nodes which are satisfying all your constraints.
So here I have a question. So
Yeah.
so for all the constraints here, each one of it could be correspond to one label here, right? So one
Yes.
type of label.
Yes. Yes.
Okay, you are doing something like a regression task, kind of,
Yes.
and this could be multi-dimensional regression.
Right. Right.
Okay,
Right.
I see. I see. Okay,
Right.
and maybe a part of them satisfy this, and then you will throw them into the simulator to gather the ground truth result. Is this?
No.
No.
Because again,
Yeah.
even if they are 20, they are still much, right?
Mhm.
You don't want that time to be wasted as well.
Mhm.
So take those 20, put an input bound on those on the feature side, right? And run a D algorithm on it. So what the D algorithm is going to do is, it is going to minimize your objective function, or let's say a generic term should be optimize your objective function, right? And generate one or many new solutions based on the convexity of your objective function.
Mhm.
But those solutions will not have labels. Correct? How do you get the labels? So this problem again becomes something like this, where you have some labels, most of them unlabeled. So, but you have already trained your GNN. So that graph surrogate model will be used to put the labels corresponding to those new solutions.
So can you see how you get this new solution? Like a kind of here solution, I guess you mean a design of a type of
Yes,
design.
the labels like the gain, UGB, those are my solutions.
So basically, GNN output will be a bunch of like labels, or you call it a
Yes,
solution.
yes, yes.
Suppose 20 of them satisfy the hard constraint there,
Right.
and then you are saying you want to run some like a D algorithms, right?
Right,
What
right.
is D
A
algorithm?
differential evolution algorithm. So
Okay.
that's a evolutionary algorithm that's a heuristic one, right?
Oh, okay.
So because you don't know the form of your objective function, right? So you cannot decide on previously that whether it is going to be convex or not. So all your KKT conditions and all of those things, they may or may not work there,
Mhm,
right?
mhm.
So you want to have a heuristic algorithm which will satisfy
So
that.
that is much faster than the simulator. I
Yes,
know, like
yes,
but a
yes.
heuristic or traditional heuristic
Correct,
algorithm, right?
Correct.
Okay, run on those, and then you will select the best one.
Then you will get the new ones, correct? That solution will
Why?
be one.
Why this is a new one? Yeah.
See,
So here,
Huh.
where I have 20
correct?
different circuit instances,
Yes,
right?
Correct.
And the GNN output tells us they satisfy this hard constraint,
Correct.
right?
Right.
And then you will use a heuristic, which
Mhm.
I know is much faster, but maybe slower than GNN, but faster than simulator.
Mhm.
Run on those, maybe get some like some objective or some objective value for this circuit.
Right.
And then why you say there's a new design or new system?
Because
yeah.
those samples were not previously available within my graph, right? Because I have what I
Then how UGN can infer over them?
see, the thing is, because we have used different algorithms like GAT and SAGE, right? So
Mhm.
these are inductive in nature. So even though these samples were not previously available in my sample, once I freeze my model and do a label prediction corresponding to a new graph, it is most likely going to give you the right solutions. Because I understand when you're saying that how can we get those solutions? That is going.
So
Yeah.
my understanding is all. So you actually have a series of graph circuits, like
Correct.
your series of circuits,
Correct.
and all of them are like previously already designed, and each of them correspond to a node in the graph,
Correct.
right? So and you select 20 of the nodes,
Right.
right? Although you don't know the ground truth, but you have the heuristic to run to collect some information
Yeah,
for
but the
this.
heuristic is not going to generate the labels. It will generate the new features.
What kind of new feature?
See, the thing is, now let's say you have the stack, right? Okay, these 20 nodes corresponding to that, you have the labels as well, correct?
Mhm,
Because we have done it a label prediction. Now, let's say these are the nodes which are satisfying all your constraints,
Mhm.
right? Just focus on this particular area, the feature one. Okay?
Okay.
Take the bounds on it. Understand where the feature vector is moving, right?
Okay.
Right? Within that particular bound, run a D algorithm.
Oh, so the D algorithm is not try to infer the label of this 20, but more like you kind of its input is some parameter space.
Exactly.
Okay, and Jin is trying to give you a more sharper parameter space, and then you put that into the curious. Okay, I see. I see the point.
And then you
And-
get the new labels.
Yes.
Yeah,
for
yes,
the ones.
yes,
Yeah.
yes.
Okay, I
Very
get the
cool.
idea.
Okay.
Thank you.
Thank you very much. I'm reporting a bit from the conference. Is it okay if I record? Perfect. Okay. I've no clue what the core problems in collaborative filtering are.
Okay, it's basically typical way to solve problem in recommender system.
Yeah.
So in recommendation system. So what we do basically is we're trying to find a better loss in recommendation.
Okay.
And this loss can achieve better generalization ability. The meaning of generalization ability means for some external data set, like when the testing and training are different, the distribution are different,
Okay.
and still perform not that bad. That is
Really?
generalization ability. Well, in recommendation system. So how could we achieve this?
But what do you mean the test and training is different? So let's say Netflix, right? They recommend
Yeah.
movies to users.
No problem.
What would generalization mean?
Yeah, you will change something like the taste of yourself.
Okay.
Will divert, right? Based on this, because we collect the data like
Yeah.
in a period,
Yeah.
and then we use this data to train the model and predict. But when we predict, it's future,
Okay. Yeah.
and your taste will change.
Okay.
So this basically is generalization ability and the difference between training and testing.
Okay. And how do you tackle that?
Solve this problem. Basically, recommendation is all about ranking like
Yeah.
one by one.
Yeah.
What we truly interested, which one is the first, which one is the second one.
Yeah.
The order is all we care about, right? And how do we do this? We use some laws. Laws is a ranking.
Okay. Yeah.
We have like point-wise laws, pair-wise laws like BPR, or influence laws. Recently, very, very popular one in self-supervised learning or contrastive learning. And for influence laws, actually what we have is we have multiple negative J here.
Yeah.
And we have a unified, predefined physical domain, which means we want J to be far away from the positive line.
Okay.
This is only constraint. But
Yeah.
this is not that good for us because suppose some J, I truly dislike this J.
Yeah.
Then I want this J to be far away from positive one. But suppose I might like this J, although it is negative.
Yeah.
Right? This one might be the positive one for me, and we want this J maybe closer. So suppose for each J, we have this delta here. Oracle delta, I am the god. I find a fine-grained ranking criterion for this. Well, the J2 is more likely to be the positive one, J1 is far away, so J2 is the first one, right?
Yeah.
So suppose I have this fine-grained ranking criterion.
Yeah.
Just like this, for each J, we have the Oracle delta J here.
So you know how bad something is. Yeah.
How dislike,
Yeah.
how much dislike, degree of
Yeah,
dislike
yeah.
here, and we call it hardness, whatever.
Yeah.
It's some degree of hardness or degree of dislike. And but just based on this fine-grained ranking criterion, we can directly obtain this mean part of our new laws here.
Yeah.
And the only difference between this new laws and our influence of the old influence laws, this one is actually here, the delta J.
Yeah.
For each negative J, we have some degree of dislike.
So you just weight the negative samples
Yeah.
by the like the hardness in some way.
Yes.
Okay.
But how to learn this? We
Yeah.
are not the god. We need to learn this
Well,
stuff.
you are not.
Yeah.
I mean.
Yes, you may. But still, we need to learn the delta J.
Yeah.
How to? Here, we use adverse training to learn this delta J. So we maximum to learn this delta J and then minimum theta to train the recommender. And you may ask me why you use adverse training, why it works, right? And we theoretically prove that when we do this, actually we are equivalent to solving a distributional robust problems.
Yeah.
This distributional robust problems is designed for OOD, out of distribution problems.
Yeah.
It has already been proved that it can achieve better generalization ability.
Okay.
So basically, we design a new loss here.
Yeah.
Very similar to the old influence E1, slightly changed, and it can theoretically prove that it will achieve better generalization.
Very cool. So help me understand this. So I maximize here over a delta. Where is the delta here? That's okay. So this is all the different deltas. So I'm trying to see what is the worst case hardness assignment
Okay.
for
For DRO here as well. Like,
Yeah.
For the I mean, I proved this. This is a DRO,
Mhm.
right? The definition of DRO. And here we have a KL divergence between P0 and P.
Yeah.
P0 is training data. You can think like this.
Yeah.
We have learned from P0. However, we have no idea about the testing, which is P.
Yeah.
And DRO assume one thing, like in an area like eta,
Yeah.
when the P is not that far from, or
Yeah.
in an area of eta, we can achieve not bad worst
Okay.
case.
So you assume the worst case that's still in some region,
Yes.
and then you try to find the parameters that are optimal for the worst case, and that guarantees that even if my tastes change in the future, it's still okay, because even if my tastes change in the worst possible way, you're still robust.
Yes, right.
Okay. Well, very excellent. Very excellent.
You got 100%.
Thank you.
And
Thanks, I'm Yannick. Nice.
Yeah.
Very nice. Very
Thank
nice.
you.
What's your name?
My name is Anjang. I'm the
Anjang.
yes, first off.
Very cool.
Thank you so
Thank you
much.
so much. I'm doing a bit of reporting. Is it okay if I record here?
Sure. Yeah.
Okay. Okay. Could you let me know a bit what your research
Ooh,
is
now the
about?
pressure's on, huh? Yeah, for sure.
No worries.
Are you yourself familiar with knowledge distillation or anything?
A little bit.
Okay.
Little bit.
How about spectrum clustering?
A little bit.
Okay. Yeah. So what we're trying to do here with knowledge distillation is saying that I've got some teacher model that's really large, and I need to teach a smaller student model.
Yeah.
Instead of just trying to get the student model to learn exactly the outputs that the teacher model gives, I'm going to take pairs of inputs and make sure that the similarity between what the student model gives on those inputs is similar between the student and the teacher model.
Yeah.
This relation matching.
Okay.
I want similarity between FSXI and FSXJ to be close to the similarity that's between given by the teacher model.
Do you have a reasoning why you would want that? It seems like an unnecessary indirection. Why wouldn't I just match the FSXI to FTXI?
Yeah, well, that's originally what knowledge distillation
Exactly, yeah.
doing. Empirically, people have been seeing this work better. Sometimes the thing was nobody had really given a theoretical interpretation for why this was working better.
Okay,
Kind of like how you're saying, why should that work better?
Yeah.
An idea for us comes down to essentially that it's like a spectral cluster.
Okay.
That by looking at all these pairwise similarities,
Yeah.
as long as the teacher model has learned a good enough graph structure, then the student model can learn probably from that graph structure as it's well clustered enough. The idea here, so the main two takeaways being that what is RKD really learning? It's helping us to learn clustering structure, a spectral clustering as you define things in the right way, which I can get to.
Yeah.
But then the second one, as I have that clustering, or that ability to capture that clustering structure, if I include RKD in a semi-supervised learning framework,
Yeah.
then the amount of label points I need is reduced because the clustering structure, in addition to the label supervision, it can leverage both of those
Yeah,
to only
I see.
need
I see.
less. And so the graph structure, we're assuming that the data that our sample has come from is this population level. And this population level graph that's revealed by the teacher model. So these edge weights between inputs are revealed to us by the teacher model.
Yes.
What that means over here, at this population level induced graph, if I consider minimizers of this spectral clustering error, this is one of the ways you can write spectral clustering. Minimizers of that inside of a function class, such as like neural networks. So that's FLX is minimizers of this clustering error inside of a function class. So FLX, that subset of the functions. If this graph right here is given to us by this from the teacher model, then this can be rewritten in this way that looks like this spectral contrastive.
Okay.
Spectral kind of loss. You can define a clustering error for a set of functions like that. That comes down to how big the set of points that are mismatched between the true clustering and what F suggests the clustering is.
Yeah.
So with that clustering error here and all these definitions, we can say if the graph given to us by the teacher model is good enough or clustered enough, then the clustering error on that set of functions that minimizes this clustering error is going to be small.
Okay.
That's
And the L here is going to be the networks we train for the student to match the teacher graph, or
this is saying at the population level, assuming that we'd have everything. But
okay.
Yes, the student model we learn on the whole population.
Yeah.
We got to learn it on the whole population would be this.
Yes.
This right here is then going from the population to just a sample from that. Yeah. You're getting a Rademacher complexity or class coming out there. But so all this at the end of the day tells us RKD is essentially doing spectral clustering.
Yeah. Okay.
This result over here then says, as I come into semi-supervised learning, leveraging RKD as essentially like a regularization, then as long as everything's nice and clustered, I can get nice generalization guarantees and sample complexity guarantees saying that I only need really a linear number of labeled samples. Essentially, in the best case scenario, I just need one label point per cluster to have a good...
because you have the whole graph, you have the cliques or whatever given.
Exactly. It's like I'm adding in my empirical risk. But this minimization problem, it's as if I'm taking F inside of these minimizers of the spectral clustering. Then I don't need that many labeled points. So.
Okay. Very cool. What do you then recommend? Let's say, what kind of problem would this now be best on?
From a practical standpoint, albeit we weren't doing it in a specific application, but where it would seem to fit for me would be, I have a teacher model that's just really large, but I have a lot of faith that teacher model is going to give me a good idea of clustering structure. That these outputs are going to be that it has really learned dogs are different from cats, and that really on that global level. In that case, I can use RKD to make sure my student model matches those pairwise similarities, and that will help me to learn the clustering structure that would be given to you by the teacher model. That the teacher model has learned, I guess.
And the similarity here, is that any similarity, or does it need to fulfill some stuff?
That's a good point. I don't know of like necessary and sufficient conditions on what that similarity needs to be. There's different ways of measuring similarity in the literature, but we specifically used this just square differences.
Very cool. Oh, thank you so much.
Yeah, of course.
Very interesting.
Yeah,
thanks.
Appreciate it. Thanks.
Keep going.
Have a good one.
Can I record while you do it?
Yeah, sure.
Okay.
So the idea is that that you have all these multiple methods, right? The models which are trained for classification purposes. Now, if you try to apply some kind of inversion attack and you try to invert the gradients, you can reconstruct these signals back, right? That's your original, and those are the reconstructed images. But unfortunately, what you see is when you take a given two images, original and reconstructed, you see that according to this metric, it is showing that these are the most similar ones, like because these metrics are often not correlated. So what you're saying is that according to the human, this was the most similar to this, so your privacy leakage was happening. But the metric suggested that this metric was actually that these were the most similar ones. So you picked up a wrong candidate. So what you're saying is that again in this setup that you have original image, and according to the human, this information leakage was happening more for this one. But the algorithm, the current matrix picked up this one. Likewise, what you're saying is the same thing. That means that the current matrix, if you would use they often break. So you need a universal metric, and that matrix that coherently and consistently works across picking up the right candidate samples, which actually leaks or doesn't leak the information. And that's what we're also showing here in the PSN or MSC. Often two metrics do not even correlate, and there's a huge mismatch. Like one metric says that that yes, things are similar, one says no. And therefore you need one coherent metric. And what we propose is that we get our dataset annotated according to the human observer. And once you have annotated your dataset, that some information leakage is happening for given image, while for second one it is not, you basically prepare that and you train a triplet loss. So for a given original sample, you have anchor and you have a positives and negatives, which are the information leakage happening, and for one not happening. So those are the pairs, and then you basically train that with the anchor, positive and negative, and you train the triplet loss. The model is trained, let's say. Now in the test time, what you do is that you push this two corresponding images, original and reconstructed, and you produce a feature vector, and you get a similar. For two feature vectors, you can produce a given score, right? Our generated scores relates very well to the human observer's standpoint. That if our metric says that these two things are not similar, it relates very well what human agreed with. If it says that the score is very less, then it aligns again very well with the human observer's standpoint, and that's what we are showing. In that space, when we say that, we also compared with PSNR, MSC, and other metrics from a structure similarity or trainable methods as well. Our method consistently performs well. In addition, if you see an interesting thing here, is that for a given data set, if you pick up a FID, for example, it is not necessary that the same metric performs well for the other method. For every other data set, some other metric performs well. That requires even more importance or more need that you pick up one metric that is universal in nature. And that's what we show that it consistently performs well, just not for inversion gradients method, but you could also use different attack methods here, and it's the same. For any attack method or different data sets, consistently performs well. Additionally, if you consider a setup where you use, for your model training, you could use different type of methods or different networks as a backbone. It again performs consistently well. Together with, if you change from triplet loss to contrastive loss, it again performs well. And the results improve consistently if you increase the training number of samples. And further, we also show another use case is that if you do not do the training and if you just try to do a retrieval, the retrieval tends to say, or the scores are somehow, for similar, dissimilar, they tend to have no order. And that's why they all are like all over. But in our setup, given our trained method, once you have trained it, then the most similar ones and the most dissimilar ones get further away. That clearly shows that the more information leakage is happening here and less information leakage is happening as you move across the line. And that's more or less the paper. And additionally, one thing that we have done in our paper, in our setup, we had binary setup where you lose information or you don't lose information. But this could be done over a scale from 1 through 10. A lot of information leakage is happening over a scale. That is something that we still want to work on in our next papers. That's overall the paper. Thanks.
Excellent. So you published the data set here?
Yeah, we do.
Okay.
The paper, the data set is already accessible.
Yeah.
Additionally with the labels. Yeah. And I think that we will also share all the codes and all the necessary things that we have shown here.
Very cool.
Yeah, that's the plan.
Awesome. Thank you very
much.
much.
So much.